students, so today we will solve some problems on mathematical induction. So first of all, what is a mathematical induction? Given a mathematical statement, say S of n, we prove that this mathematical statement is true for all n greater than or equal to 1. That is for all positive integers. You can also say it as natural numbers. So we prove that this S of n, that is a mathematical statement, that S of n is true for all n greater than or equal to 1. Okay. So here we follow some steps to say that this statement is true. So step 1, we will be proving for one particular point. Step 2 is called as an induction step, where we will be assuming something. Step 3, based on the assumption which we have assumed in step 2, we will prove that it is true for all n greater than or equal to 1. So if we consider S of n to be some statement given to us, we follow 3 steps here. So step 1, we verify that S of n naught is true for n equal to n naught. So S of n is a statement given to us. We will prove that S of n naught is true for n equal to n naught. For instance, that is in particular, we take S of 1 is true. That is n is equal to 1 we take, and we prove that S of 1 is true. That is step 1. Step 2 is also called as an induction step. So in this induction step, we will assume that S of n is true for n is equal to k, where k is an integer which is greater than or equal to n naught. That is, previously if we have taken n is equal to 1, here we say that k is some other integer wherein k is greater than or equal to 1. So we assume that S of n is true for n is equal to k. That is step 2. Step 3, here what we do is we show that this S of n is true for n is equal to k plus 1. Okay. So what are we doing here is S of n is a statement given to us. In the first step, we prove that S of 1 is true. Whatever the statement is given to us, in place of n, we will substitute 1 and we will prove that step 1 is true. In step 2, which is called as an induction step, we will assume that n is equal to k and we will prove that S of k is true. We will not prove, we will just assume that S of k is true. Step 3, we will take the step 2, that is, we will use step 2 and we will show that S of k plus 1 is true. That is where n is equal to k plus 1. So just 3 steps. We will solve few problems on mathematical induction so that it will be easy for you to understand. The first problem is to prove that by mathematical induction, 1 plus 2 plus 3 plus so on plus n, which is equal to n into n plus 1 by 2, is true for all n greater than or equal to 1. So this is nothing but sum of natural numbers. So let's see how to prove this statement. So we have the statement S of n given to us, that is 1 plus 2 plus 3 plus so on plus n is equal to n into n plus 1 by 2. This is the statement given to us. So step 1, what do we do? Step 1 says we have to take n is equal to 1. In the procedure I have explained you. So S of 1 you take, and in place of n we have to substitute 1 alone. So if you see in the statement S of n, when you take n is equal to 1, you will have in the left hand side only this number, that is 1 alone. So 1 is equal to, because your n is equal to 1, so when you're substituting n is equal to 1, you get only 1 in the LHS. In the RHS, in place of n, if you have 1, you get 1 into 1 plus 1 by 2. So this will be equal to 1 into 2 by 2. So you get 2 and 2 gets cancelled. So 1 into 1 you get 1. That is, you're getting LHS is equal to RHS. So S of 1 is true because you have LHS is equal to RHS. Therefore, you can say that S of 1 is true. So this is your first step. Second step is known as the induction step. Step 2. So in step 2, I told you it is an inductive step, or you can also say it as induction step. So here we are assuming that n is equal to k. Suppose that s of k, that is in place of n, you are substituting k. So what do you get? 1 plus 2 plus 3 plus so on, plus in place of n we have k, that is equal to k into k plus 1 by 2. Just in place of n, you are replacing it with k. So you are telling that this is true for all positive integers k greater than or equal to 1. This is our inductive step, wherein we have just assumed for n is equal to k and for k greater than or equal to 1. In step 3, what did I tell? In step 3, we have to prove that s of k plus 1 is true. So based on the assumption which we have assumed in step 2, we will prove that s of k plus 1 is true here. So s of k plus 1 means what? In place of n, you have to put k plus 1. But you take that the assumption which we have assumed in step 2, that is 1 plus 2 plus so on plus k plus 1 is equal to, in place of n, I told you that you have to put k plus 1. So what do you get? K plus 1 into k plus 1 plus 1 divided by 2. Okay, remember that you had n into n plus 1 by 2 in the RHS. N into n plus 1 by 2, I have just written k plus 1 into k plus 1 plus 1 by 2. In place of n, just k plus 1 is written. That's all. But we have to prove this. Okay, based on the assumption which we had in the previous case, that is in step 2, we will prove this. So from step 2, what we have? We have that 1 plus 2 plus 3 plus so on plus k is equal to k into k plus 1 by 2. This is what we had from step 2. Now here you add k plus 1 on both the sides. Okay, k plus 1 on both sides. So what do you get? You get 1 plus 2 plus 3 plus so on plus k plus 1 you have. This is equal to k into k plus 1 by 2 plus k plus 1. This is what we have now. Let us solve this RHS value. So this will be equal to k into k plus 1 divided by 2 plus, let me take this as k plus 1. Now taking LCM, what do you get? You get k into k plus 1 plus 2 times of k plus 1 whole divided by 2. So here when you are taking the LCM, this 2 goes here, isn't it? So we get 2 into k plus 1 whole divided by 2. Now here this bracket terms k plus 1 and k plus 1, these two terms, that is this term and this term, is common. So let us take it outside. So what do we get? K plus 1 we have taken common. Now what is left in the first term? We have k. What is left in the second term? We have 2 whole divided by 2. This is what we have. We can write this as, this is equal to k plus 1 This k plus 2 can be written as k plus 1 plus 1 divided by 2. K plus 2 can be written as k plus 1 plus 1 whole divided by 2. So this generally in terms of n into n plus 1 by 2, we can write it as k plus 1 into k plus 1 plus 1 whole divided by 2. So in the LHS, what do we have? 1 plus 2 plus 3 plus so on plus k plus 1. So this in the LHS we have this term k plus 1 into k plus 1 plus 1 by 2. This we have in the RHS. So we proved this mathematical statement. We proved this mathematical statement. So this statement we proved for k plus 1. So if you check the last step, the last line of the proof, you can see that in place of n we have k plus 1. So hence the proof. Hence we can write that s of k plus 1, that is 1 plus 2 plus so on plus k plus 1 is equal to k plus 1 into k plus 1 plus 1 whole divided by 2 is true, but for what? For all n greater than or equal to 1. So this is the proof by mathematical induction. Okay, so this is how you have to prove the problem. Let us try solving few more problems on this. So the second question here is to prove this given statement by mathematical induction. So here the statement is summation 2i minus 1 is equal to 1 plus 3 plus 5 plus so on plus 2n minus 1 is equal to n square. So this is nothing but sum of odd numbers, you can say. So this is equal to n square for all n greater than or equal to 1. This has to be proved by mathematical induction. So what was the first step? So proof. So what do we write? First we take the statement s of n, given statement as it is. No need of writing this summation. We'll just take 1 plus 3 plus 5 plus so on plus 2n minus 1 is equal to n square. So this we have taken. What was our step 1? Step 1 was in place of n you have to put s of 1, so that you get 1 is equal to, that is only one number you have to take. In place of n, if you substitute 1, what do you get? 2 into 1 minus 1, that is 2 minus 1, that is equal to 1. So that is your LHS. Okay, or if you are not sure about it, take only the first term from the s of n. So 1 is equal to, in your RHS, in this RHS, substitute 1. So you get 1 square. So this implies 1 is equal to 1. So your LHS is equal to RHS. Therefore, we can say that S of 1 is true. Now, what was the step 2? So step 2 is known as the inductive step. So in inductive step, what do? In place of n, we substitute it for k. So from the statement we have s of k is to 1 plus 3 plus 5 plus so on plus, if you see here, you have 2n minus 1. We are substituting for k. So you will get 2k minus 1 is equal to k square. So this is your assumption step. So induction step, that is you're assuming s of k is to this term is equal to k square is true for all k greater than or equal to 1. This is step 2, that's all. Now step 3, what we are supposed to do? In place of k, we are replacing it with k plus 1. So k plus 1, s of k plus 1, that will be 1 plus 3 plus 5 plus so on plus 2k minus 1 plus 2 times of, means I'm taking this step here, the next term will be k plus 1, right? So here you have up to k, when you're taking k plus 1, you will have the other term as k plus 1. So here you substitute 2 into, in place of this k plus 1 minus 1. This is our next term. This will be equal to k plus 1 the whole square. Since this is a summation series, up to k means you will have 2k minus 1. The next term, k plus 1, is the next term. So if you have k plus 1 term, in place of k, substitute for k plus 1, so that you get 2 into k plus 1 minus 1. This is equal to, in the RHS, in place of k, substitute k plus 1. So you get k plus 1 the whole square. So this is step 3. Now we have, what do we have? From step 2, what do we have? So as I've told you, to prove step 3, you have to use step 2. So use that step 2, that is 1 plus 3 plus 5 plus so on plus 2 times of k minus 1, or you can write this as 2k minus 1 also. Yes, 2k minus 1. This is equal to k square. So this is our step 2 here. Now what we have to get? We have to get 2k minus 2k plus 1 of minus 1. So this term we have to get. So what do? We add on both the sides 2 times of k plus 1 minus 1. That is, we are adding this term. Okay, this term we are adding both the sides, because we have to prove this statement, right? This statement we have to prove. So we will add this term both the sides. Let us see what do we get. So add 2 times of k plus 1 minus 1 on both sides. On both sides. So what do we get? 1 plus 3 plus 5 plus so on plus 2k minus 1. This is one term, plus 2 times of k plus 1 minus 1. This term, both the sides you have to add. So this is equal to k square plus, again the same term, 2 times of k plus 1 minus 1. So with this we have to prove this statement. Okay, so if you compare this statement and this statement, if you see in the LHS, you have the same terms. You have 1 plus 3 plus so on, this complete term you have here in the LHS. So no need to touch LHS, only the RHS you have to alter. That is, you have to get k plus 1 the whole square. So if you solve this this part, you have to get k plus 1 the whole square. So let us solve for RHS. So this will be equal to k square plus 2k plus 2 minus 1. This is equal to k square plus 2k. 2 minus 1 is 1. So what is this? K square plus 2k plus 1. You can write this as k plus 1 the whole square. So if you expand it, what do you get? A plus b whole square form. A square plus b square plus 2ab. So if you expand this, k plus 1 the whole square, you get a square plus b square plus 2ab. You get back the previous term. This term you get back. So therefore 1 plus 3 plus 5 plus so on plus 2 times of k plus 1 minus 1 gives you k plus 1 the whole square. So this is what we are supposed to prove, and we got it. So this is true for all n greater than or equal to 1 by mathematical induction. So this we have proved. So just a recap for you. So this was the statement given to you. So listen carefully. This was the statement given to us. So what did we do in the first step? In place of n, you had put n is equal to 1. So n is equal to 1 you had taken in the first step. You got 1 is equal to 1 and you proved that s of 1 is true. In step 2, what I told you, you have to put s of k. That is in place of n, substitute for k. So you got 1 plus 3 plus 5 plus so on plus 2k minus 1, that is equal to k square. So from this step you are putting n is equal to k. Fine, this was our inductive step. In step 3, what we have to do? In place of n, we have to take k plus 1. So you got s of k plus 1 is 2, 1 plus 3 plus 5 plus so on plus 2k minus 1 plus the next term, that is 2 times of k plus 1 minus 1. So here in place of k, you substitute for k plus 1, so that you get 2 times of k plus 1 minus 1, that is equal to k plus 1 the whole square. Fine. So we have from the inductive step, that is from this step, you wrote this. Now you have to add 2k plus 1 minus 1 on both the sides. So you can ask me, how do we know that we have to add this term? So here in step 3, when you replace n is equal to k plus 1, you are getting this as another term, an extra term you get. Okay. So this term has to be added on both the sides. So we had added that. So on adding that, you get k square plus 2 times of k plus 1 minus 1. So if you solve for the RHS, you are getting k plus 1 the whole square. So this is what we had to prove here. Okay. So 1 plus 3 plus 5 plus so on plus 2k plus 1 minus 1 is equal to k plus 1 the whole square is true for all n greater than or equal to 1 by mathematical induction. So hope you have understood. So we will solve another problem here. So here in the last you can write s of n is true for all n greater than or equal to 1. Okay, fine. Let us solve another problem. So the next problem is sum of squares of natural numbers. So you might know this result, n into n plus 1 into 2n plus 1 by 6 is the sum of squares of the natural numbers. So this we have to prove for all n greater than or equal to 1. So we will prove this using the mathematical induction. So what was our first line which we used to write? We will take the statement given, that is s of n is equal to 1 square plus 2 square plus so on plus n square is equal to n into n plus 1 into 2n plus 1 divided by 6. So this is the statement given for all n greater than or equal to 1. Now what was our first step? First step is in place of n, substitute 1. So see, always we will be using this statement and we will be proving for n is equal to 1 and we will assume for n is equal to k and we will prove again for n is equal to k plus 1. So in our first step, s of 1 we take. So that is 2. So in your LHS, in this statement, if you see s of 1, that is the first term, only this term will come. So you are going to get 1 square is equal to, in your RHS, that is in this term, substitute n is equal to 1. So what do we get if we substitute n is equal to 1 in the RHS? We get 1 into 1 plus 1 into 2 into 1 plus 1 whole divided by 6. So this will be equal to 1 into 1 plus 1 is 2, 2 into 1 is 2 plus 1, 2 plus 1 divided by 6. So that will be equal to 1 into 2 is 2, 2 plus 1 is 3 divided by 6. So you get 6 by 6. So if you cancel, you're going to get 1 here. What is 1 square? 1. So s of 1 is 2. 1 is equal to 1 you got. So therefore 1 is equal, see in all the cases 1 is equal to 1, not that way. You have to prove that LHS is equal to RHS. So therefore S of 1 is true. Okay, S of 1 is true. Now step 2. What is our step 2? Step 2 is our inductive step. So in our inductive step, what do? We assume that S of k, that is in place of n, we are substituting k. That's all. So S of k, that is 1 square plus 2 square plus so on, plus instead of n square I am writing k square. That is equal to, if you see here, you have n into n plus 1 into 2n plus 1 by 6. So in place of n, I am substituting for k. So what do we get? We get k into k plus 1 into 2k plus 1 whole divided by 6. Fine. So we are assuming that this is true for k greater than or equal to 1. This is our assumption step 2. Step 3. So the major part of your working depends on step 3. So step 3, what do we want to prove? To prove that S of k plus 1 now. Instead of k, here you have k plus 1. So that is 1 square plus 2 square plus so on plus k square plus k plus 1. The whole square is equal to, see here. So this was our statement, right? So in place of n square, we have to substitute k plus 1. That is in place of n, you have to substitute k plus 1. So I am writing 1 square plus 2 square plus so on. In place of n, I am writing k plus 1 the whole square. So the preceding term will be k square, right? Here you have 2, the preceding term was 1. Similarly, here you have k plus 1, the preceding term will be k. That's all. So this is equal to, in place of n in the RHS, here in place of n you are substituting for k plus 1 now. So what do you get? K plus 1 into k plus 1 plus 1 into 2 times of k plus 1 plus 1 whole divided by 6. So here this we have to prove. This statement has to be proved. Fine. But what do we take? We have from the inductive step what we had? We had S of k, isn't it? So that you take here. That is 1 square plus 2 square plus so on plus k square is equal to k into k plus 1 into 2k plus 1 whole divided by 6. So this is what we have from the induction step. What has to be proved? We have to add one more term in this S of k. That is this term we require. So up to k square you want k plus 1 the whole square. This term you want. So what do? We add k plus 1 the whole square on both the sides. So your next step will be add k plus 1 the whole square on both sides. So what do we get? We get 1 square plus 2 square plus so on plus k square, let it be as it is. We are adding k plus 1 the whole square. That is equal to k into k plus 1 into 2k plus 1 divided by 6 plus k plus 1 the whole square. Okay, we have to prove this step. We have to prove this. So you have to do something in your RHS, some simplification in your RHS to get this step. That is, this step you have to get. Okay, so let us do that. So here this is equal to, see, don't touch the LHS term, because LHS, what we have to prove in LHS, it is there already. Only the RHS term has to be altered so that we get in place of n k plus 1. So here let us take the LCM. So LCM 6 goes here. So you get k into k plus 1 into 2k plus 1 plus 6 times of k plus 1 the whole square whole divided by 6. So this will be equal to, so here if you see this k plus 1 and here k plus 1 whole square, two terms are there. So k plus 1 you can take it as a common. So you get k plus 1 in brackets whatever the term is left, that is k into 2k plus 1 is here 6 into k plus 1, one more term is there. Okay, here you had square term, right? So one term we have taken out, so one term is pending there, this whole divided by 6. So here let this k plus 1 term be as it is. We will simplify for the square bracket term. So if you multiply this, what do you get? 2k square plus k plus this term 6 into k plus 6 into 1 plus 6 whole divided by 6. So this is equal to k plus 1. Again here you have 2k square, k plus 6k, that will be 7k plus 6 whole divided by 6. Now just factorize this square bracket term. Okay, so let us factorize the square bracket term and then let us get back to this step. Let it be as it is. This you have to do it in your working part, but let me do it here. So we have 2k square plus 7k plus 6. How do you factorize them? So 2 into 6 you will take, that is 12, and this 7 you will write it here. I hope you know this factorization part. So you have to have two numbers such that when you get two numbers such that when you multiply that two numbers, say a and b, you have to get 12. When you add that two numbers a and b, you have to get 7. If that is not the case, if you are not able to find them, then you have to use the formula method, that is k is equal to minus b plus or minus root of b square minus 4ac divided by 2a. I hope you all know this. So from this equation, what is a? A is 2. What is b? B is 7. What is c? C is 6. So this is equal to minus b. So that will be minus 7 plus or minus root of b square, that is 7 square 49 minus 4 into a value, a is 2 into c value, c is 6 whole divided by 2 into a, that is 2. So this is equal to minus 7 plus or minus root of 49 minus 4 2s are 8, 8 6 are 48 divided by 4 you are getting. So this is equal to minus 7 plus or minus 49 minus 48, that is 1, root of 1 is 1 divided by 4. So what do you get? This is equal to minus 7 plus 1 by 4, or you have two values here, minus 7 minus 1 by 4, two values you have. So k is equal to, because you have plus or minus here, so one value will be with plus, one will be with negative. So minus 7 plus 1 by 4, that is minus 6 by 4 or minus 8 by 4. So this is equal to minus 3 by 2, as 2 goes here 2 times, 2 goes here 3 times, here 2 goes 2 times, 2 goes 4 times, or 2 goes 1 time, 2 goes 2 times. So minus 2. So this or minus 2. So here you have k as minus 3 by 2 or with minus 2. So from this, how will you write it as a factor? You had the equation as 2k square plus 7k plus 6. I want you to write this as a factors. Okay, this as some factor. So how will you write? You have k is equal to minus 3 by 2 or k is equal to minus 2. So this you can write it as this term. If you take 2 here, you will write it as 2k, and this minus 3, when it goes to the left hand side, you will get plus 3. Here I'll tell you how. So k is equal to minus 3 by 2. If you take 2 here, that will imply 2k is equal to minus 3, or 2k, this plus 3, when you take it to the left hand side, you get 2k plus 3 is equal to 0. This is one term. The other one is from here only, k is equal to minus 2, right? So when you're taking minus 2 to the left hand side, you get k plus 2 is equal to 0. So these are the two factors. So you can write this this term you can write it as 2k plus 3 into 2 plus k, or 2k plus 3 into k plus 2. Okay, so this is how you will be factorizing this term. Fine. See, when you multiply this term, these two terms, you have to get back this equation again. Try multiplying them. 2k into k, 2k square. 2k into 2 plus 4k. 3k into k plus 3k. 3 into 2 plus 6. So what you are getting? 2k square plus 4 plus 3, that is 7k plus 6. See, you are getting back the same previous equation. So this term 2k square plus 7k plus 6, this can also be written as 2k plus 3 into 2 plus k. That's all. So that factorization, how do you get that factors? So by just viewing also you can write the factors. If you are not able to write this factor, then you have to solve for k. Then you can take k plus of that value and k plus of the other value as the factors. So now this equation, this term here, 2k square plus 7k plus 6 can be written as what? K plus 2 into 2k plus 3. So that is our next step. So this term can be written as k plus 1 into k plus 2 into 2k plus 3 whole divided by 6. So now if you remember the statement in the RHS, what do we had? We had n into n plus 1 into 2n plus 1 by 6. This term we had. So in place of n, I want k plus 1. So in such a way you alter this. So we will get k plus 1 into k plus 1 plus 1. We can write 2 as 1 plus 1, right? So that is what I wrote here. This into 2k plus 1 no, I'll write it as 2k plus 2 plus 1. This 3 I'm writing as 2 plus 1 whole divided by 6. This I can write it as k plus 1 into k plus 1 plus 1. This here take 2 common, 2 times of k plus 1 plus 1 whole divided by 6. Now you see here, you compare this with this term. In place of n, what do we have? We have k plus 1. In place of n in the second term, we have k plus 1. In place of n in the third term, you have k plus 1. So wherever you have n, we have k plus 1. So therefore, our statement, that is 1 square plus 2 square plus so on plus k plus 1 the whole square, that is equal to k plus 1 into k plus 1 plus 1 into 2 times of k plus 1 plus 1 whole divided by 6 is true for n greater than or equal to 1. Okay, so somehow we proved that the third step, that is s of k plus 1 is true. So final step, what we will write? Therefore, we can say that s of n, that is 1 square plus 2 square plus so on plus n square is equal to n into n plus 1 into 2n plus 1 divided by 6 is true for all n greater than or equal to 1. Fine. So similarly, I want you to prove for sum of cubes of natural numbers. So this you prove, that is sum of n cube. So this you prove by mathematical induction. This will be your homework problem. So you can prove this. We will solve one last problem on this mathematical induction. So I hope you have understood the previous problems. So similar to that, this is a different kind of a problem. So here also you have to use mathematical induction to prove that 2 to the power 2n minus 1 is divisible by 3. That is, 3 divides 2 to the power 2n minus 1 for all n greater than or equal to 1. So try solving along with me. So here the proof. Well, let us follow the same procedure as before. I repeat once again. So here we will write the statement s of n first. Step 1, in place of n we will substitute for 1 and we will tell that s of 1 is true. Step 2, inductive step, we will assume that n is equal to k, that is s of k is true for k greater than or equal to 1. Step 3, we will use step 2 to prove s of k plus 1 is true. That's all. So once we prove all this step 1, step 2 and step 3, we can say that s of n is true for all n greater than or equal to 1. That is what we are going to do here. So listen carefully. So first, what do we write in our proof? We write the given statement, that is s of n is 2, 3 divides 2 to the power 2n minus 1 for all n greater than or equal to 1. This is the given statement which we have. So what is step 1? Step 1 I told you, in place of n substitute for 1, s of 1. So that is 2, 3 divides 2 to the power 2 into 1 minus 1. This is 2, 3 divides 2 to the power 2 into 1. What is 2 into 1? That is 2 only, minus 1. So that is 3 divides 2 square is what? 4 minus 1. So that is 2, 3 divides 4 minus 1 is 3. Will 3 divide 3? Yes, right? 3 divides 3. So therefore I can say that s of 1 is true. Okay, done. Step 1 is done. That's all. Step 2. Step 2 is an inductive step. Inductive step, what do? We just assume here. We are not proving anything here. We just assume that s of k is 2. In place of n, just substitute k. 3 divided by 2 to the power 2n we had, right? We will write it as 2k minus 1 and we assume that this is true for all k greater than or equal to 1. Okay, so this is our step 2. That's all. Just we have assumed and kept it, but we will use this for our step 3. So what is our step 3 now? Step 3 is we have to prove. What is that? What we have to prove? We have to prove that s of k plus 1. Okay. Third step, remember, k plus 1. In place of n, substitute k plus 1. So that is 2, 3 divided by 2 to the power 2 times of k plus 1 minus 1. So this we have to prove. How do we prove that? Using step 2, we will prove this. Step 3. So here you don't add any terms here. We will just prove that this s of k plus 1 is true. 3 divides 2 to the power 2 k plus 1 minus 1 is true. We will prove it as it is, but don't add any terms here because there is no summation given here. We have something divisible by some term. So no need of adding any terms here. Only if you have a series or a summation, then you can add the step 2 to step 3, that is k plus 1 term you can add to s of k, but here no need of adding any terms. I'll tell you how to do it. So here this is to 3 divides here 2 to the power, this term you have, right, 2 into k plus 1, just multiply them. What do you get? 2k plus 2 plus minus 1, write it as it is. So this is to 3 divides, see this term 2 to the power, see 2 to the power m plus n, this I can write it as 2 to the power m into 2 to the power n, isn't it? So when the bases are same, you can add the powers and that's what you got, 2 to the power m plus n. So 2 to the power m plus n can be written as 2 to the power m into 2 to the power n. So I will write this term as 2 to the power 2k into 2 to the power 2 minus 1. So this is to 3 divides 2 to the power 2k, let me write it as it is, into, what is 2 square? 4 minus 1. Okay, so this is to 3 divides 2 to the power 2k. Can I write 4 as 3 plus 1? This minus 1, let it be as it is. So this can be written as 3 divides 2 to the power 2k into 3, that is I am multiplying this term with this term plus this term with this term, that is plus 2 to the power 2k, this minus 1, let it be as it is. Okay, done. Now this is to 3 divides, I have two terms here, one is 3 into 2 to the power 2k plus I have the other term, that is 2 to the power 2k minus 1. Two terms I have here. Fine. Now from step 2, that is from your assumption, that is this step 2, if you see here, what do you have? 3 divides 2 to the power 2k minus 1. So that term you have here. 3 divides 2 to the power 2k minus 1. But you, yes, 3 divides 2 to the power 2k minus 1. So that is fine. Will, just check, will 3 divide 3 to the 3 into 2 to the power 2k? Will it divide? See here you have something that is multiple of 3 here. So of course if you divide 3 divided by 3 into 2 to the power 2k, what do you get? 3 goes in 3 once and you will be left out with 2 to the power k. We do not know that 2 to the power k also might be divisible, but it is divisible at least once. Okay, 3 divides 3 into 2 to the power 2k, yes, it is divisible. So now you can say that 2 to the power 2k into 3, this is divisible by 3 and 2 to the power 2k minus 1 is also divisible by 3. This is from where? From step 2. Okay. So therefore, hence I can say that sum of 2 to the power 2k dot 3 plus or and let me write it as and 2 to the power 2k minus 1 is divisible by 3. Okay, so each term separately they are divisible, so the sum is also divisible by 3. Therefore I can write s of k plus 1, that is 3 divides 2 to the power 2 times of k plus 1 minus 1 is true. Is true. Therefore, I can say that s of n, that is 3 divides 2 to the power 2n minus 1 is true for all n greater than or equal to 1 by mathematical induction. That's all. Okay, so if you have series, you have to add k plus 1 on both the sides. If you don't have series, try to solve this RHS and say that it is divisible. Just separate the terms and you say that they are divisible by 3. That's all. Okay, so I hope you understood.